Okay, I'll wait about a minute or two to get started here. Okay, let me know if anybody's got any questions ahead of time right now. We're kind of in the penultimate class of the term. Things are winding down a little bit. Anybody got anything? Hopefully I don't get too much sound through the window here. It's actually legitimately hot enough to need this window open over here. She'll see if the screaming children liven up our talk today. Or the screaming cat, depending on where she's at. Oh, you're correct. I still have not shown you the cat. I will have to show you all the cat. I don't know where she's at. Normally she would swing by at some point, but when it's next convenient, either this lecture or the last lecture, I will wave the cat around on camera. She's a good cat. Okay, I guess I'll start yammering here. Kind of light attendance today, but that's not unexpected. I mean, I'm sure everyone is just out traveling after the long weekend and everything like that. Anyway, so it is week 9, and we're into the one of the kind of like tangential topics of this class, right? So we've gone through sort of key things up till now, and now we're kind of delving into something that is, it's entirely possible to do all the work you would ever do in R, in all the classes you do and all that kind of stuff, without ever using anything in this class, right? This is sort of an optional topics type one, because we're gonna be talking about mapping and geospatial data, okay? So basic plan for today is I'm going to talk about what I would call basic mapping in ggplot first, which is really just feeding ggplot raw coordinates in whatever format they are, typically latitude and longitude, but you could use other sort of coordinate data. Talking about mashing up coordinate data with actual maps, so raster maps, that is maps obtained from things like OpenStreetMap, Google Maps, Stamen Maps, and things obtained from the ggmap package. And then I'm going to talk about labeling points and using the ggrepel package to make it so labels don't overlap with each other. And then we'll transition to more advanced mapping. More advanced mapping in R is pretty much always going to be based around using either R's SP package or SF package. Because SF is the newer standard, I'm only going to talk about SF in this class. And SF, or simple features geometry, is basically the same way geometries typically are stored in other GIS software, things like Arc Platform or QGIS, right? And R handles these in the same way, and you can do most of the same stuff. And then I will talk about a special application of working with the SF package and its sort of like framework, which is using Tidy Census to obtain and work with Census Bureau data. That is US Decennial Census, ACS, and some related data sets. Okay. So if you're going to be doing serious mapping in R, especially geostatistics, this is probably the book to get and to work with. So this is Applied Spatial Data Analysis with R by Baivan, Pobesma, and Gomez-Rubio. So Baivan and Pobesma are the main authors of R's original geostatistics and geospatial platform called SP, and they're also authors of the SF package that we'll be using later. They wrote the tools, so they know how to write a book on it. And this is sort of a one-stop shop for geostatistics. This could be the only book you get in geostatistics, and it will take you through almost everything you'd need to know before you get to things like random Gaussian field models or something like that, which is really advanced. Okay, and if you want to know about that stuff, you could go take John Wakefield's CSSS508 Statistical Methods for Spatial Data. This is a pretty challenging class. I wouldn't recommend doing it until you've finished like your full normal graduate stats sequence, and it would help to have taken a class in maximum likelihood almost for sure, and maybe Bayesian methods. But that class will teach you the most like cutting edge spatial statistics stuff that's practically used in sort of applied situations. Okay. For getting up to speed with other GIS platforms, that being QGIS, ARC, CSDE does offer workshops in these things. My personal preference is for QGIS because it's open source free software and I abhor proprietary software. But if you're going to go work in the business world or something like that in the private sector, most of them are going to be using ARC. So that's a good reason to pick up ARC. If you're doing it mostly for your own research in universities, QGIS is the way to go. ARC is great if you have access to it. Somebody else is going to pay for your license. You might as well pick up ARC. Yeah. Okay. So I'm going to get into basic mapping first. So back in week 5, we looked at different types of incidents, that is calls to the police department and their responses to those calls from a single day. If you remember, those data had some information on where they occurred. They had things like latitude and longitude. We're going to look at those for examples today. So I load up Tidyverse here. I load in the data. I just pull it down straight from the website. You can see there, it's a small data file. And these are what those data look like, right? So each one of these is an individual police event. So if you kind of look at an observation, you might see something like it has some sort of unique number here, like a CAD number. Technically speaking, the number you actually be looking for would be the general offense number, which uniquely identifies the event. There would be something like a description, like a theft, a car prowl. It's a particular type of theft. It's people breaking into cars, right? It's part of a certain subgroup and total group of offenses. It occurred at a given time, at a given location, but the location data is provided in a number of different ways. If you're working with the police department, you might work in zones or beats or sectors. If you're interested in where something happened in plain human language, you might look at the 100-block location. So this is South King Street and 8th Avenue South. If you're familiar with the layout of Seattle, you know exactly where this occurred. But more useful to us for mapping and stuff is going to be the actual longitude and latitude values here that will allow us to precisely plot the locations of these things, okay? So this sort of data like this is basically what the type of data I work with every day, because I mostly work with police data and I work with the police department a little bit. So, you know, this is nice because it provides you with longitudes and latitudes, okay? I'm not going to cover in this lecture how you get coordinates from data that don't have them. So if you have things like just this human language, South King Street, 8th Avenue South, you absolutely can convert that into a longitude and latitude using something called reverse geolocation or reverse lookup. But it's a bit of a pain, requires some finickiness. I have a lot of experience in it though, if you want to do that sort of thing, right? Yeah, packages that can convert not dates, but those like written language, dates to coordinates. Well, I mean, if you think about it, dates are on sort of a type of Cartesian plane. It just tends to move only in one direction. But
that is not what I meant.
I know.
I just meant addresses to coordinates. But
yeah,
then you
absolutely.
answered my question as I typed it incorrectly. Sorry.
Oh, yeah, absolutely. So the package that I'm going to show you for mapping, ggmap, actually will do this. It will convert things like South King Street and 8th Avenue South into coordinates for you. It just requires a little bit of processing and setting things up. Basically, if you could open South King Street and 8th Avenue South in Google Maps and have it show you the right location, let's actually try that. Let's say, paste that in. I'm gonna say paste this, Seattle, not Seattle, Seattle, Washington. If that gives me the right intersection, and it does, then the ggmap package would give you the correct coordinates. Because the ggmap package just queries Google like that. And if you look at Google, the longitude and latitude are right here up in the address. So if you need to pull them like that, you can get the ggmap package to extract the longitude and latitude of anything you give it. So you can code it like this. And I just recently did a racial bias in Terry stops report for the Seattle Police Department. And the Terry stop data doesn't have latitudes and longitudes, just has these rough addresses. all 28,000 of those I had to code like this through ggmap using the API. I don't show it in this class. I'll probably add it one of these future ones. But you know, it's entirely possible in the package I'm showing you. Okay, moving on. So coordinates like longitude and latitude can just be provided in the AES for a ggplot like any other x and y values. They're locations on a Cartesian plane. Coordinates work like any other coordinates, right? This is sort of ideal when you don't need to place points over some map for reference, right? I could take the SPD raw data that I just loaded up and just say x is longitude, y is latitude, do a geom point. I say here coordinate fixed. Coord fixed makes it so the space between y units and x units is the same. This isn't ideal for latitude and longitude because the width between longitudes changes depending where you are on the planet. You get further up north and there's smaller distances. But in this case, it kind of works. And then I just plot it out here, right? So if you're familiar with the shape of Seattle, and most of you are, you'll probably recognize Seattle here, right? So the Bay is right here, downtown Seattle is here, there's a gap right here where Lake Union is at, Lake Washington is over here, the university is a gap over here. The university is a gap over here because the university has its own police department and the SPD does not respond to events in it, so it kind of looks like a gap, okay? And generally this is an outline of Seattle. So for any person who has not been staring at maps of Seattle for a reasonable part of their life is not going to recognize the shape over here as anything, right? And for wanting to know where any given cluster of points are, it's kind of hard to tell, right? This is the sort of thing you would probably want plotted over an actual map of some kind, right? Sometimes you don't have a map to plot things on or you don't care about it. Maybe you're working with something like well drilling data and you don't actually care about like the normal like geographic references. You just care about the distance from different things or something like that. Though for that, you probably want something like topography. Anyway, if you don't want to care about a reference, it's fine. But most of the time when we're working with social data in space, we want to see what it is in reference to, okay? So to do that, we're going to use the ggmap package. So ggmap is a package that works in conjunction with ggplot to plot your spatial data directly on top of images of maps that are downloaded from Google Maps, OpenStreetMap, or Stamen Maps. And sometimes they'll add additional map services to it, but the main ones you'll see are Google Maps, OpenStreetMap, and Stamen. So what this package does for you quite sort of like easily is it will query a server for a map at the location and scale you want. So you could, for instance, just say, I want a map of Mary Gates Hall, University of Washington. It will give you that map. Or you could give it some geospatial data that has latitude and longitude points. It will figure out where those points are on a Google map, say, obtain a map of the correct cutout, basically, pasted in the background. Okay, so it will plot that map. It'll plot that raster. That is, it's sort of an image, like a JPEG, a PNG or something. It's not like a vector image, if you're familiar with the difference. It will plot that in the background as an image in your ggplot. You can then add ggplot layers, things like points, density plots, and text annotations on top of this map. It also offers some additional functions for interacting with Google Maps. For instance, you might want to do something like get the distance, either in time or actual distance, between 2 points for bicycle riding, for cars, for walking, right? It can query all these things that are normally available in the Google Maps API. This is kind of handy for doing certain types of analyses. Maybe you think, for instance, statistically speaking, what matters about the impact of some place to another place is not its linear distance, but rather the distance you would have to walk to get there. You might want to use walking distances instead of their linear distance, right? And that is as the crow flies. Okay. One thing about ggmap, if you want to use maps from Google Maps now, and I say now, it's really been about the last year and a half or 2 years, it requires that you set up an API key with Google. Now, getting an API for Google is kind of a pain. So to get an API key with them, you have to give them a credit card number. The reason for this is that if you make a sufficient number of queries, and it's a lot of queries, you do have to pay for it. Practically speaking, most of the time you're not going to be making enough queries to ever have to pay the money, but they need to have that there to enable you to have access to the platform. Signing up for Google API also requires that you sign up for their general API for all of their products. The result of this is that you will get spammed with emails about ridiculous Google enterprise software nonstop once you've signed up for their API key, even if you're only interested in using it for maps. This is really annoying, but it's the only way to get Google Maps. I often use OpenStreetMap or Stamen for the hell of it. They work perfectly well, but sometimes the Google Maps are just nicer than the alternatives. Don't they already have all of our info? Yes, but this is really about giving them permission to use it. They know these things already, but if you give them permission, then you can't sue them when they use your credit card. That's really all it is. Okay. So installation, you can install the ggmap like any other package. So install.packages ggmap will do it. The thing is, though, is packages like ggmap, and often packages that deal with things like social media data, like Twitter and stuff, their APIs will often change frequently, right? So, there's children coming outside. 1 second. When I hear the howling of children in the distance, I know it's time to close the window. They're being taken for their regular walk. Anyway, so because these APIs change frequently, that is the Google Maps API, OpenStreetMap API, and this is way worse for social media APIs, sometimes you'll find the functions don't work. You may have to go and download the newer development version of it on the author's GitHub, okay? So if you want to download the development version, and I usually am using the development version of most of these cutting edge packages, you can use the remotes package to do this. So this code right here will check to make sure you have the remotes package installed. If not, it will install it. And then it will go and download the ggmap package from the author's GitHub. It'll just go and grab it. So I do this routinely to update packages and make sure I'm on the cutting edge packages. Sometimes they'll have bugs in them. You can always go back to the one that's available on CRAN by doing install.packages ggmap. Okay. Now we'll load it up. One thing about this, if you install something directly from GitHub, very often it will require compilation. There's instructions for enabling package compilation on the course website right up near the top. This is pretty easy to do for Macs. It takes a little bit of installation on Windows computers because they don't natively have a C compiler. Okay. So quick maps with ggmap. So ggmap has a function called qmplot, which stands for quick map plot. This will automatically set a region for a map based on the data that it finds that you give to it. So if I say qmplot, my data is my SPD raw data, my X is longitude, my Y is latitude, I can then give it a color and an alpha, it will figure out using the longitude and latitude where it needs to find this map, that is where to center the map and plot it on top of it. So by running this simple qmplot here, we get a nice map like this. Every one of these dots is an individual event in our SPD data plotted on top of an actual Google Maps sort of like hybrid map of the Seattle area, right? So it figures out the map to draw, the shape of it and everything from your longitude and latitude, so you don't have to go and download a map separately or something like that. And you can tell our data are plotted in the correct locations on here because you don't see a bunch of events sitting out in the water or something like that, right? They sort of follow the major streets and the contours of terrain for Seattle, okay? One finicky thing about this, if you want to set all of the dots or whatever to have the same color or the same alpha, you need to specify these in an I here, which basically says this thing here is not a variable name, but is rather something I want to set all of the points to. It's just some finicky syntax, and that's the way ggmap is. You can just copy this code if it's weird. Okay. Any questions about this? Yeah, it's pretty straightforward. ggmap just kind of works. It's kind of nice.
I have a question about your last slide. So you use the kind of the latest version because that's generally more stable because it changes more often than other packages. Is that the kind of reasoning?
So there's a trade-off. The newer package will have the newest package will have the up-to-date API. So it will be able to download the data properly. In this case, the data is that background map. So sometimes you'll find that the CRAN version, that is the one you get from install packages ggmap, will give you some weird error like API error or something. And that's because Google has updated their API and the software hasn't been updated to compensate for that change. The development version will probably work with the API well, but it may have some buggy new features or something. So it's a bit of a trade-off. Generally, one of them is working perfectly at any given time.
Okay.
Yeah. I usually like to almost always use the development version of something like ggmap because I know how to deal with the errors if there are any, and it usually just always works for me. But stability varies, you know, it's just, yeah. Okay. Anything else? Okay. So the QM plot and QMap. So QMap, I didn't show that before, but what QMap is you just give it a latitude and longitude point or a search term, and it will just draw the map. It doesn't plot your data on top of it, it just draws the map, okay? These are wrappers for an underlying function called getMap, which actually retrieves that map layer. It has a lot of options which you can pass to either QMplot, QMap, or just get directly. You can give it a location. For OpenStreetMap and Stamen maps, you can just give it a longitude and latitude of where you want the map, and it will do it. For Google Maps, you can give it a Google Map search term. So whatever you'd punch into Google to search for something, and it will produce the same map that maps.google.com produces. Literally the same map, because all it's doing is querying Google Maps for you. You then provide a zoom level. So zooms are kind of an arbitrary unit. They don't correspond to some like simulated elevation or something. The gist of it is 3 is like a full continent. 1, I guess, is like the entire planet. 10 is about city level. 21 looks inside of buildings. So if you have like a Google map that actually has the building plotted, like Allen Library on campus or something, you could get inside of it. If you had some data like individual movement data from sensors or something, you could plot it inside of a building. There's a source argument, which you can say, give me a Google map, OpenStreetMaps, or Stamen maps. And then there's map types, and the map types are specific to the sources. So Google has maps like terrain, terrain background. You can use satellite maps, road maps, hybrid maps. Hybrid is kind of like one of the default types of maps you get on maps.google.com. Stamen maps have these sort of artsy maps, like things that look watercolor. Toner and toner background kind of look like they're in sort of a urban planning kind of aesthetic. They're kind of nice. I like to use toner maps a lot. Color is nice. You can specify whether you want the maps to come to you in color or in black and white. This is nice because if you make a beautiful color map and you put it in your journal article, your journal will butcher it and manually convert it to black and white, and it will look like garbage. It's better to just give them the black and white map so they don't butcher it for you. Okay. Yeah. So you can do a lot of normal ggplot style things on top of these QMplot and QMap layers, okay? So if I call QMplot, but I don't give it a geometry, I could add other geometries other than dots on top of it. So in this case, I say, I want to do my QMplot of my SPD raw data. I don't want a geometry. I just say geom blank, which is a way of telling it, don't plot any dots, just get me the map. I say X is longitude, Y is latitude. My map type, I say toner light here, but I can see in the background, this is clearly a Google map one, so I forgot to specify the source was OpenStreetMap. It just defaulted to a Google map. Darken 0.5 just makes the map 50% darker. Okay, this is a way that if the map is too bright for the data you want to show, you can make the background map darker. I then add to it a stat density 2D. This is a 2-dimensional density plot, otherwise known as a heat map, right? I say here that the fill for my heat map is going to be a statistic calculated by stat density, which is the level. This right here is sort of an arcane syntax in ggplot, which is a way of specifying that I want it to use its own calculated level density statistic. So stat density 2D calculates this thing for us. It's kind of the same way that geom bar calculates a bar height based on the number of observations. That is kind of like a histogram rather than using the raw data. I then say the geometry to use is polygon. You could use polygon. You can also use line if you want outlines. I then just say I want it partially transparent. And I say color equals NA here. I don't remember exactly what that is. I think I'm suppressing the outline color. And then scale fill gradient allows me to control the color gradient of this heat map, basically saying I want low concentrations to be white, middle to be yellow, and high concentrations of points to be red. Okay? So what I get over here is a heat map of crime incidents in Seattle. So we kind of see density-wise, everything is sort of centered on downtown. I could do things like change, if you're familiar with densities, I could do things like change the kernel and stuff like this to make this more useful. But unsurprisingly, most crime incidents on a given day occur pretty close to downtown Seattle. So here was a question. Since the low on your legend is white, it doesn't show up against the white background. Is there a way to outline the legend color bar so it's clear that white is an option? I think there is, but I forget exactly how. Probably. In this case, actually, I think technically the end of the scale is actually coming all the way down to here because it won't plot any kind of density, I think, where there are 0 events within the kernel. So it's actually omitted down here. And that's just something particular about stat density 2D. Technically speaking, there actually isn't any white area, I don't think. It just so happens, I think, on this scale that the minimum thing it's picking up within any kernel is about 50. I'd have to play with it to see. I don't use stat density 2D too often. I prefer things like hexagonal binning or something. Yeah. Okay. So moving on to something slightly different. Let's label all the assaults and robberies that happened in downtown and put some labels on them. Haven't used labels in this class too much, but it's a useful thing to know about. So the first thing I'm going to do here is I'm going to filter my SPD raw data down to just the events occurring in downtown. So to do this, I just eyeballed it on a prior map. So over on this map, I've actually suppressed the latitude and longitude graticules. Those are the lines that go across the map. But I know, well, so I actually just kind of know this because I spend way too much time in Seattle data, that downtown is approximately between 47.58 and 47.64 latitude and between -122.36 and 31 longitude. It just happens to be where downtown Seattle is. So I'm going to say, take my SPD raw data and filter it down to this location. This will give us data only in the box kind of around generally downtown. I think it'll dip into Capitol Hill a little bit, being that far over to the east. Or sorry. Yeah, okay. So then we're going to make a data frame of just the assaults and robberies. So I say here, the assaults in the data is just my downtown only data, filtered down so the event clearance group, that is the type of crime, is either assaults or robberies. And then I mutate out a label, which is just equal to the event clearance description. This is just giving me a shorter thing I can reference in the next plot. Okay, so the event clearance description is just a longer title. So instead of being assaults, it's going to be assaults dash like aggravated assault or assault with a weapon, robbery dash strong arm robbery or something, if you're familiar with different types of robbery, which I am. Then we can plot it with labels. So what I want to do here is I'm going to do my QM plot. My data are all my downtown crimes, not just the assaults and robberies. I say X is longitude, Y is latitude. My map type here, I say tone or light, but again, I forgot to say source equals OSM, so it's a Google map on the background. It used to, in a previous version of ggmap when I made this, recognize tone or light was supposed to be an OpenStreetMap, but eventually OpenStreetMap and Google had one particular map with the same name, so they made you do source, and I forgot to change it. Silly Chuck. Anyway, fire brick red dots, partially transparent, but then notice what I'm doing here. I'm saying geom label to add labels to this plot, but the data is the assaults data instead. So I'm limiting my labels down to only the data set of assaults and robberies. So I have all the crime data here, but the labels only correspond to the assaults, right? I then say the label is going to be equal to assault label, which is just the name of the type of crime, and size 2.5 increases or decreases the size of the labels. So I forget if this was me making them a little bit bigger or me making them a little bit smaller, but it was one of those things. And then what we get over here are labels for the individual things. So there was a strong arm robbery up here, some other type of assault here, armed robbery, some sort of assault here, strong arm, okay? So you'll see immediately that the problem with sort of doing labels on something like this, which is like clustered and sort of data all on top of each other, I can't read these labels back here, and I can't even tell how many labels are there, right? It might be that there's a ton of different robberies occurring here, but these labels have covered them all up, right? Overlapping is something that happens commonly with labels if you don't do something about it. Okay. Another thing about these labels is that I believe the center of the label, like exactly right here, by default is where that point is. On a map like this, it's actually kind of hard to tell what location these labels are referring to because they are covering up the street location they occurred in. This might not be ideal. You might instead want to offset them and like draw a line to them, which is something you can do in geomlabel. Okay. So if we want to deal at least with the overlapping thing, we can bring in another package. What I'm going to do is we can bring in the ggrepel package. So if you want to use this, you'll have to do install.packages ggrepel. So what this does, if you load up library ggrepel, is it gives you an alternate version of geomlabel and geomtext geometries. So instead of saying geomlabel like I did on the previous slide, I say geomlabel_repel. Otherwise, I give the entire thing the same arguments, except for one thing I've added here, which is segment color equals black. What segment color equals black will do is if geomrepel has to move the label a ways off of its point, it will draw a line to the point it's referring to. So what geomlabel_repel has done over here is it's made these labels repel each other as best as they can, right? So this is a constrained space because I'm plotting it in this little sub window over here in my slide. But basically the strong arm robbery assaults other strong arm robbery here. These have been pushed away from each other to try and make them a little bit more readable. And if you look, I don't think I can zoom in on these. I can't. Okay. If you look, you'll see there's a black line right here. There's also a black line right here. What this black line is a line being drawn from this label to the actual point that that label is associated with. So I believe it's actually this label occurred right here under this particular one. This one, assault's firearm involved, is pointing to this dot right here, okay? So geomlabel_repel does its best at trying to separate all the labels, and then if it has to push them far enough, it draws a little line to them. This is kind of handy and something you might want to use if you've got overlapping labels, but you still might have to do some manual tweaking of them to make them look good. Okay? Any questions about labeling or anything I've covered so far? It's kind of hard to tell if anybody has anything or if it's good because none of you have your cameras on today. It's deeply upsetting. Okay. Well, one of you has a camera on. I like the thumbs up. There we go. Peer pressure. Okay. Okay, so let's move on. So the next segment of this, the more entertaining, more interesting one, is the advanced mapping section, which is essentially just using R for GIS, for Geographic Information Systems work, right? So to get into using R as a GIS platform, I need to walk you through some terminology first. If you're somebody who already does geospatial analysis, this stuff is redundant to you. And if you hear anything I say that's kind of wrong, you can correct me if you have a lot more experience in this. I'm not a GIS expert. I am a GIS hedge wizard who taught himself most of these things. I do a lot of geospatial analysis, but I don't have any like deep professional expertise in it. Okay, so the main things I need to talk about and explain are simple features. That is the sort of type of geometry data storage method that are used by the SF package, but also QGIS, ArcGIS is an ISO standard for data storage. Coordinate reference systems, or CRSs, and shapefiles. So, SF. Up until recently, which I guess was about a year and a half ago, the main way you would work with geospatial data in R was through a package called SP. SP is a great package with a lot of support out there, and it's the package that is used predominantly in Bivand and Pabezma and Gomez-Rubio's book. It's an excellent package for geospatial data analysis. It was written by geographers, okay? They know what they're doing with geospatial data. The thing is, though, is that SP does its best to store geospatial data in a format that works in R. Okay. The thing is the format that they chose to store things in SP is not similar to the data storage methods used in most GIS packages. It tends to be bulky and complicated. Okay. The idea in SP is that if you have something like a polygon point, right? So imagine you have polygon point, but polygons, right? Let's say you have like a rectangle or a trapezoid. It has 4 points and 4 lines to it. In SP, normally you would store that polygon as 4 rows in your data, 1 for each point in it, and you would just say that those points are connected. Now, if you can imagine the shape of something like the state of Washington, you can imagine that there are a lot of vertices, that is a lot of points in the state of Washington. Depending on your resolution, there may be millions of points defining that. It doesn't seem ideal to store data on the state of Washington as 1 million individual rows in your data just to get that resolution, right? This is sort of a problem in sort of the way that SP often stores its data. SF does not work this way. SF stores any arbitrary geometry, regardless of number of its points, as a single element in a data frame. This is more complex to do, but it makes things more compact. Okay. So the more recent SF package, the only thing I'm going to cover today, implements the GIS standard of simple features. Okay, and when I say GIS standard, I mean it is an International Standards Organization standard for data storage, which means pretty much all geostatistical and geospatial software uses simple features as its general method of storing data. Okay, if you want to know more about it, you can click on Learn Tons about simple features. I'm only going to get into it a little shallowly. A nice thing about SF is that SF is much newer than SP and has been integrated into the tidyverse, which includes things like a geometry specifically for plotting geospatial data called geomsf, and most of SF data plays nicely with dplyr, tidyr, and stuff like that. So you can keep using your dplyr functions. This is not true with SP. SP often gets rather upset with some operations you might do in dplyr. Modern tidyr using pivot wider and longer, however, gets a little bit upset with SF, but that should be fixed relatively soon. Okay, so this package SF is new, but it is expected to fully replace the SP package. The authors of it are the same authors and contributors from SP, but they've added new developers like Hadley Wickham, Grolem, and some other people from the tidyverse, okay? Because SF is this new standard, it's the only thing I'm going to cover in my class, the only thing I'll provide support for. So if you used SP in the past, I would recommend migrating to SF. If you encounter some way to do something online like Stack Overflow and somebody offers an SF way and an SP way, use the SF way. It's probably going to be easier for you to handle. Okay, so we can load up library SF. And next, I want to talk about simple features. So a simple feature is a single observation with some defined geospatial location or locations, okay? Features in R are stored in special data frames of the class SF, and they have 2 properties. They have a geometry. So every observation in your data must have a geometry. If you have data that has a missing location, it can't be in your SF data frame. You cannot have missing locations in an SF data frame. Everything has to have a location. Geometries are the properties that describe the location as in where it is, usually on Earth. You can work in SF data sets, of course, that maybe there are other planets, but also maybe they don't exist in real space. You might make an SF data frame that describes things in network space or something like that. You can totally do it, but most people are working with real coordinates on real physical coordinates. Geometries are usually 2 dimensions. Usually there's a X and a Y. That could be a latitude and a longitude, but they don't necessarily have to be. But simple features supports up to 4 dimensions. So obviously a 3rd dimension might be height. It's quite common to include Z dimensions for topography in your data. But they can also include a time dimension. Your 4th dimension could be time to do full time space data frames. You rarely encounter these actually used in all 4 dimensions in SF, but it's possible to do it. So the geometry is stored always in its own reserved column, almost always named geometry. This is a list column. So let's say that you have state data in your data frame. You've got 50 US states. No matter how complex the geometry of that state is, its boundary might be defined by 1,000,000 points. All 1,000,000 points will be stored in a single cell of your data in the row for that state in the geometry column. This is done using something called a list column, meaning that individual cell contains an entire list. And as we've seen in this class, lists can be crazy and contain tons of nested data. Okay, so this geometry column contains really complicated stuff. The nice thing about SF is you will generally never have to directly interact with this list column. Just know that if you attempt to modify this column, it is not a normal R data frame column. It is a weird thing that R will get real upset about you trying to use normal data frame tools to manipulate. Normally, just leave that geometry column alone. Don't mess with it. It will bite you, okay? This geometry column also contains a defined coordinate reference system that tells R, and sort of tells everything you're working with, what the coordinates refer to. With latitudes and longitudes, your points will refer to spaces on the spherical grid of the planet. But you might instead be working with a CRS that its units are in something like feet, and it refers to the center of Washington State. This is a projection I commonly work with, which is NAD 83 Washington North, which is sort of a coordinate reference system that refers specifically to the northern half of Washington State. Its units are in feet, and it's flat instead of being spherical like latitude and longitude. Talk about CRSs in a minute. Okay, so all that stuff is in the geometry. Every other attribute, that is every other column of your data, is just an attribute in the data frame that is other columns. All characteristics of the simple feature that you're looking at, that is things like maybe the population of the state or something like that, will be stored as other columns. These are all the non-spatial measures. They're just standard data frame columns, and you can work with those data frame columns the way you would work with any other normal column in a data frame using dplyr or whatever like that, right? So don't mess with your geometry column unless you know what you're doing. Attribute columns, that is every other data frame, do your normal stuff with them and it will work. Okay. List columns, I will say this, if you want to do something like even remove the geometry column from your data frame, you'll need to use a special function even to pry it out of your data frame. It is something special and reserved and requires a special function even to delete from your data normally. Okay, so coordinate reference systems. Coordinate reference systems will specify the location on Earth the coordinates you're using are relative to, right? So everything you plot on an XY grid, right, is some Cartesian plane. On a normal plot we know what 0, 0 refers to. But 0, 0, that is the center of your Cartesian plane on Earth, doesn't have any inherent meaning. You could pick arbitrarily any point on the planet to use as 0, 0 because it's a sphere, right? So coordinate reference systems tell R and tell your computer basically where the 0, 0 point is on the planet, and they also tell it how to project that sphere, if you want to project it, into a flat plane. Like maybe you're familiar with Mercator projections, right? A old way to convert the sphere into a flat map so you could draw maps. That is a type of projection, and its 0, 0 point is a particular location. The 0, 0 on a Mercator projection is the prime meridian in the equator, right? But that's an arbitrary point that some Europeans decided was a good way to divide up time and space, right? You can pick up any point you want arbitrarily. Okay. The most commonly used coordinate reference system you'll probably encounter is one called WGS, which I think is World Geological Survey or Geographic Survey 1984. This is the standard you'll see for Google Earth. Also, the Department of Defense, and because the Department of Defense, GPS satellites, right? So the Global Positioning System works in WGS 84. So basically everything you encounter commonly, so administrative data that's not specific to like a state or a country, is probably going to be WGS 84 format. Longitude and latitude, that kind of thing, WGS 84. Okay, so there are two common ways to define a CRS in the SF package. The most common way and the easiest way is with using something called an EPSG code, okay? These are just numeric codes which refer to predefined coordinate reference systems. So for instance, if you want to convert your data to WGS 84, the code for it is 4326. You can just say at CRS equals 4326, and R has a lookup table and will go get the appropriate projection to convert your data to WGS 84. There are thousands of these projections, and you can just go Google EPSG codes and you can look them up and search for things. The other way you can define a projection or a CRS in R is using proj for strings. Proj is a basically a software utility for converting coordinate reference systems to one another. The proj for string is a way to tell proj how to do these conversions. Okay, it is a text string of parameters that define a CRS, usually relative to WGS84 because it's sort of the default. So here's an example our proj for string. This is for NAD83 NSR 2007 Washington North, which is what I use in my police data. It is this big old string that looks like this. Okay, everything in the string has a particular meaning. For instance, this latitude 1 means that a coordinate value of 1 in here corresponds to the latitude 48.733. The 0 corresponds to this, blah, 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 blah. You don't need to know any of this stuff, but this will tell the computer how to convert any existing CRS on your computer to or from this using these parameters. All you need to know about this is if you see something that looks like this and it was provided with some geospatial data file, you can give it to SF and it will convert your data properly. Okay, it's much better to work with these codes here because you don't have to deal with this sort of thing. But if you see something like this, you can work with it. It's a proj for string. Okay. The last thing I want to talk about before we get to the fun stuff is shapefiles. Okay, so geospatial data that you'll get that is given to you or you download online is most often stored in a shapefile. Shapefiles just store geometric data, that is polygons and things like that, as vectors with associated attributes. Those attributes are variables, right? So shapefiles are typically, if you get something from like ArcGIS, QGIS, it's probably a shapefile. Okay. The thing is about shapefiles is the name lies to you. A shapefile is not one file. It's actually a zip file or a folder filled with files. So to define a shapefile properly, there's usually at least 3 individual files in there, but often there's up to like 10, right? The common ones you'll encounter and should be in there are a .shp file. The SHP file is the actual feature geometries, that is the simple features. This is a file that contains all of the vertices, the lines, and everything in your data that define all the geometries, okay? These are where all the locations are. Then there's an SHX file, a shape positional index. This is just a lookup table that allows ArcGIS or something to look up values really fast instead of having to search through this SHP file. And then there's a DBF file, which is essentially all the other columns in the data associated with these locations, okay? So you can imagine the SHP is basically your geometry column in your SF data frame. DBF is every other column in that data frame. If you are lucky, there will also be a .prj file, which defines the CRS for the file. It's really annoying to get a nice, useful shape file with all these other ones and no projection because you have no idea how to merge other data onto it if you don't know the projection. If you have a bunch of data that are in like WGS84, great format, and you want to merge them onto some administrative data, but you don't know the administrative data's projection, it can be really hard to figure out what it is. The author of the ggmap package, I actually forget if it's the ggmap guy or the tidy census guy, one of them wrote a package that, given a bunch of numeric values in your data, will guess the projection. This is actually pretty useful. If you're interested in it, you can hit me with an email. If you get some kind of shapefile that has something you really need for your thesis or dissertation, but you have no idea what projection it's in, you can use that to guess it. Okay. And this DBF file is just a standard database for file, which you could also open up normally in R using, I think it's like one of the import functions in base R will import it. Okay, so that's terminology. You just need to know that stuff if you work with geospatial things. Let's get on to the fun stuff, which is actually putting all that jargon and stuff to use. Okay. So the SF package is an enormous package, right? It is super feature rich. It has a million things in it. It's a one-stop shop for geospatial analysis, data manipulation, and things like that. This is a sample of useful functions. There's a million though. Like the stringer package that I showed earlier in the term, almost everything in the SF package begins with st underscore. So if you want to search for some function in the SF package, in our studio, you can do st underscore and then do your tab autocomplete and scroll through all of its functions. There's a ton of them though. So to read in and write shape files, it has an strread and strwrite function. For this, you just say strread and then give it the path of the .shp file in your shapefile. It figures out how to read in everything in the folder that the shp file is in and get it all loaded up into a nice tidy data frame for you. Next, geom_sf is a ggplot2 layer for SF objects. So this layer simplifies plotting anything in SF. Any SF object that you give ggplot, you can just say plus geom_sf and it figures out the X and Y, AES, all that kind of stuff for you and handles plotting it. It makes working with SF objects trivial, as we'll see in a whole bunch of options, or a whole bunch of examples in a minute. ST as SF will convert a normal data frame into an SF object. So if you have some data frame that actually has latitudes and longitudes in it, and you want to convert it to an SF object, you can just pipe it into ST as SF, tell it which columns contain the coordinates, and it will make an SF object out of it. ST join is kind of like left join and right join in dplyr, but instead of joining by matching one column to another column, it does still works with columns, but instead of matching something like country here to country here in this other data frame, it matches by locations. Maybe you have a data frame of like census tracts and another data frame of points. ST join would allow you to join the points to the census tracts based on whether the points lie inside or not of each of the census tracts. So this is just spatial joining. This is really useful because it means that if you have any data sets at all with a geospatial component to them, you can arbitrarily merge any data, right? So very much of the work that I do, my dissertation, everything, is working with data sets which have no common indicators in them, but they have a geospatial component. And because of that, I can merge all my data together. If you can master doing sort of simple geospatial joins, you can really leverage a lot of data that can't be associated any other way. And it turns out a lot of things we're interested in have a geospatial component, so this can be pretty useful. ST transform is used to convert between different coordinate reference systems. So maybe you have one data frame that's in WGS84, it's in latitudes and longitudes, and you have another data frame that's in something like that Washington North I have. To do a join between them, they need to be in the same CRS. You could use ST transform to convert it from its existing CRS to another one. This just works by piping your data into it and giving it an EPSG code number. So you could pipe in some data in one CRS and just say ST transform 4326, and it would convert it to WGS84. If you want to remove a geometry from an SF data frame, maybe you've done your spatial join and after that you just need to run some models with it and you don't want it to have a geometry column anymore, there's a specific function for removing the geometry column called ST drop geometry. Pipe your data into it, it'll kill that geometry column. ST relate is used for computing relationships between geometries. Maybe you want something like you want to know for every given census tract in the city what its neighbors are. You could calculate a neighborhood matrix. This is useful for geostatistics. Another thing you might want to do is maybe you want to calculate the difference between things. An example I'm going to show a little bit later is we're going to subtract bodies of water from census tract plots. Okay. And another one, which I actually don't recommend using, is ST interpolate AW, which allows for aerial weighted interpolation of polygons. Maybe you have something like election precinct data, but you want to get demographic data onto it. But demographics are measured using census tracts, which don't have the same boundaries as precincts. One way to get demographic data mapped onto your precincts would be to do aerial weighted interpolation. This basically puts the polygons of the census tract and the precincts on top of each other and figures out, based on the proportion of overlap they have, how to allocate attributes of one to the other. This is sort of a nice way to merge polygonal data that have uneven overlaps with each other. The reason I don't recommend using this is there's actually a better package to do it called the aerial package that works way better for aerial interpolation. This is a common operation you'll get if you work with different delineations or different delineations of administrative data. I work with election precincts, census tracts, and police beats. I do aerial weighted interpolation all the time of all these things. Okay.
Chuck, I have a question.
Yeah.
Suppose you have data that all you have in terms of spatial information is like an address. Is there something you can use to convert that to like coordinates or something like that?
Yeah, absolutely. The way to do that would be to go back to, my recommendation would be the ggmap package. So in ggmap, if you have a Google Maps API key, you can do somewhere in the neighborhood of 10,000 address queries a day, I think, with it. And so what you could do is you could, first, what you want to do is you want to clean up your addresses. So you probably want to do something like make them all like lowercase, check for spelling, make them in a universal format. So ideally you'll have something like, number, address, or cross streets, right? And then add on to it, like paste on, if you know what city they're in, paste in the city, and ideally even like the zip code or something. You paste them all together into exactly what you would give in like Google Maps. If you can put it into Google Maps and get the correct address, ggmap will return the exact coordinates that Google Maps does. And then so what you do is then you just say, it's like, I forget what the function is. It's just like, I think it's something like geocode. It's just like called geocode or something like that in ggmap. And you can give it a vector of addresses, like a column of addresses, and just use it and mutate. Just say the coordinates equals like geocode, the column of addresses, and it will go through one address at a time, querying Google Maps and pulling down the latitude and longitude. I've used this a lot. So like I mentioned, my Terry stop data earlier was all coded this way. It works as well as Google Maps works. So the better your addresses are, the better it works. And you want to do things like after it runs, you can go and check and be like, okay, I know all my data is in Seattle. Make sure none of the points are outside of Seattle, right? You just can go search and like plot the data. Make sure you don't have a whole bunch of them sitting over in Arkansas or something like that. All right. But yeah, it actually tends to work pretty damn well. That's what I would do. And then the nice thing is that it will code it into latitudes and longitudes, which you can then convert to an SF object by giving it coordinates and telling it its projection and stuff like that. So something I do routinely. If you get into it later and you want some advice or anything like that, let me know. I'm happy to send you stuff on it. I've done it a lot. It's actually really easy and opens up a lot of possibilities for doing research with data you wouldn't normally think is geo-identified.
Thanks.
Okay. So what we want to do here is load in some data to work with. So for SF here, I'm going to work with homework 5's voting data. So we remember the mildly traumatic homework 5, where I gave you a garbage administrative data set and made you get election numbers for it. We're going to work with that. So we can get a shapefile of King County voting precincts from their GIS data portal, right? We can just pull it down and map or not map our data, but join our data onto it. So we can load that file in using stread. So I have this file locally loaded on here. You won't be able to do this unless you've also downloaded the file from the County GIS portal or downloaded my class as a zip file from GitHub. So I'm going to say the precinct shape data frame I'm going to create is stread, this shape file, strings as factors equals false. If you've updated to R 4.0, you no longer have to say strings as factors equals false. Because God has answered our pleas and gotten rid of the default conversion of characters into factors. Anyway, I'm just going to say stread this, and the only columns I care about are the precinct and the geometry. I drop all other data in here. And when you load in a shape file in SF, you get a big dump of output like this. It will say it's reading in these layers from this location. It is a simple features collection with 2,592 features of 5 fields. So it has 2,592 rows. That's how many election precincts there are in King County. 5 fields is the number of columns, okay? The geometry type is multi-polygon. This just means each one of these precincts consists of 1 or more polygons. Its dimensions are X and Y. That is, it has no height information or time information. And then it has other things like X minimum, Y minimum. These are the maximum values of the X and Y coordinates, the minimum values, whatever. And then it has a proj4 string, which if you could see far enough over here, is a full string telling us the actual coordinate reference system, meaning this shapefile had that wonderful .prj file that I always want my files to come in with. It has a proper CRS allowing us to convert it to something else. So this is all informative. You might not care about it, but this just tells you how your data loaded in. Okay. So this is the entirety of your homework 5 done on one slide, converting your data into the % Democratic votes, % Republican votes, and the turnout of votes so that we can merge this onto our geospatial data frame. So basically what I've done here is I've read in that King County elections data, done everything you did in your homework, plus kept the Republican votes. And then the important part comes down here where I just say, all of this data I've processed, I want to left join it onto my precinct shape. That is the shape file I generated on the previous slide. The thing is, if you take a normal R data frame or a tibble generated by dplyr, and join onto it an SF file, it emerges not as an SF object, but as a normal data frame. To convert it back to an SF object, you just got to say ST as SF, and it figures out where the geometry column is and reprocesses it into the appropriate object. So the result of this slide here is a data frame containing the % Democrat votes, % Republican, and the voter turnout, kind of things we calculated from that homework, but it is joined to the actual geometry of our precincts. Okay, so we can take a peek at what the data look like. If I glimpse, we have a precinct identifier. So SEA 11-1256 is one of the like 1,000 precincts in Seattle. It has this percentage of Democrat votes, this percentage of Republican votes. Its turnout was about 69%. And then this is the geometry column generated by loading in the shapefile. You'll see it looks really different from other R columns we've seen. Notice that these columns are like character data, double, which is numeric data. This one says multi-polygon US survey foot. So the actual column data type for this is a multi-polygon whose units are in US survey feet. That means a 1 unit change in this corresponds to an actual foot, US 12 inches on the ground, okay? You could have any number of other units for this. You could convert it to meters or whatever, right? Then the actual observations are things like a polygon, and then this will define the vertices of that polygon. You'll see it has lots of nested parentheses. These are defining different lines in the polygon and saying how they all connect together. You would find that for a single precinct, it might have 1,000 values sitting here in that one cell defining every vertex of that precinct polygon. You would never want to directly display or work with a single like observation here in this geometry column. There's just way too much to deal with. You just know it's there and it's working. Don't work on them directly unless you know what you're doing. I sometimes do manually construct geometries, but it's sort of like a niche thing you probably aren't going to be doing too much. Okay. The thing though here is that regardless of how many points there are in that polygon for the precinct, that precinct only has one row in the data. This makes it a lot easier to look at the values for like single precincts in here by storing all the polygon data in a single cell. It makes the polygon more complicated, but it makes the rest of the data easier to work with. And that's ideal for us because we work directly with these data values, not the geometries. Okay, so it looks like our previous data frame with some extra column added that will draw pretty pictures for us. Go. So we can plot an SF geometry object trivially using geom_sf. I just say here, I want to ggplot my precincts votes SF data. AES, I want my polygons filled by the percentage of Democratic votes. And then I just say geom_sf. In this case, I say size equals NA, just because I want to get rid of the outlines. By default, geom_sf draws lines around all the polygons. I say size equals NA. And we get this plot. This is every voting precinct that had valid data from our voting data we used in homework 5, right? So just with geom_sf, I don't specify an X, a Y, nothing else. It will just draw all those precincts because geom_sf knows how to read that polygon column in our data, and it knows how to draw every single one of our precincts properly. So we now have a nice map of voting patterns in Seattle, right? You can see where places have higher Democratic votes and lower Democratic votes. It's Seattle, so basically everything is still like 60% or higher Democratic votes, right? You have basically a couple clusters that actually have a reasonably high Republican vote. The only precinct that went like Republican is this precinct right here in Seattle, right? Basically everything else is Democratic because it's Seattle, right? But see how trivial it was to do that, right? This is SF makes plotting geospatial stuff really, really easy. It takes care of all the hard stuff. It's actually easier to plot a geom_sf thing than a normal thing with X and Y coordinates as different columns, right? It's super cool. Okay, any questions about this? Gonna have some more examples. You may actually see a slight outline around these polygons here. There isn't an outline there. The reason you're seeing that is actually because I've plotted this as a vector object instead of raster. The lines are actually gaps between the polygons that technically speaking aren't there, but the display makes it look like they're. Okay. So, oh no, that's the same question as before. Okay. So, next thing I want to talk about is the tidy census package, which will allow us to build on these SF plots I just showed you. So tidy census is a package which can be used to search the American Community Survey and decennial census data sets for variables, download them, and then automatically format them as tidy data frames ready to work with. One thing that's really cool about this package is these data frames will also include the geographical boundaries of whatever units you download, zip codes, school districts, urban areas, states, census blocks. It will include them as a geometry column in SF format. So you get all that census data you want to work with, and you get its geospatial boundaries so you can automatically merge it onto other data. Okay, if you've ever on your own gone and downloaded ACS or decennial census data from American Fact Finder, you probably never want to do that again because it sucks. This package will allow you to never do that ever again because it works directly with the census API. Okay, so this package utilizes the census API. So to use it, you need to obtain a census API key. I say here, God, I keep meaning to change it. It's been like a year here. It says I will talk more about APIs in the social media data and text mining lecture. I don't do that lecture anymore, so I will talk more about APIs next week. Basically, an API is just an application programming interface. This is a type of computer interface that exists as a native method of communication between computers. A common API, things that we'll use is based over HTTP. So if you go and search for something in Google Maps, so I have a Google Maps frame, I think, open in this browser. This stuff up here that is like S plus king plus street and then a whole bunch of crap up here, this is actually an API call your browser sends to the Google Maps API to tell it how to get this map back here and place this pin here. The API is just the method of communication that defines this way of presenting the data to it. Okay, so to use the census data, or use tidy census, you need a census API key. Other R packages that interface with websites and databases will typically use different APIs to do that. APIs make accessing data much easier for you, and they also allow websites to control access. If you want to download data from something that does not have an API, your alternative is web scraping, right? I don't talk about web scraping in this class, but if there's no API for it, you got to scrape it. Scraping is nice for circumventing access control, but yeah. Oh yeah, so that's actually a good point that Veronica makes there, which is true. I remember that now. American Fact Finder is no more. Everything is on data.census.gov. Yeah, and I guess data.census.gov is possibly better than American Fact Finder. I haven't messed with it because I use tidy census for everything. I like working with tidy census. It's not perfect, but It's pretty convenient. Okay, so one thing I will say about this. So I said before, getting a Google API key requires jumping through hoops. You have to fill out forms. They spam you with emails and they take your credit card. The exact polar opposite of the Google Maps API key is the Census API key. The Census API key is really easy to get, but the website looks like the type of website that will either steal your credit card information or send you advertisements for Viagra. I'll show you this website. This, and I'll say this before I click on it, this is a real government website for getting an API key. This is the API key website for the US Census. Does this look like something you would want to give your email address to? No, right? This is how you get weird spam, where people try to steal things from you. But no, this is how you get a Census API key. And all you have to do is say the name of your organization, which they don't check. You can put anything you want there, and give them an email address, which they don't verify in any way. So you can give them any email address you want and say, I agree to some terms of service, which it doesn't require you to read. You press a button and it gives you a permanent Census API key, which doesn't actually have, as far as I can tell, any real limits. Okay? It says .gov exactly, so I will trust it. Yeah, exactly. This is, I would normally give like a fake email address to this or something like this. I'm like, this is the website you set up. Yes, it's low bandwidth, so you can do it, but really, this cheesy website. Anyway, so polar opposite of the Google Maps API, the pinnacle of government websites. But no, it's super easy to get it. So unlike the Google Maps API, there's no reason not to get a Census API key to use it for your stuff. It's trivial and it's very powerful. Okay. So some key functions in the Tidy Census package. The one you only have to run really once is Census API key. This will install a Census API key permanently on your computer. So before using anything in Tidy Census, you just run this once and give it your API key as a string. Never include this function in something you let other people look at. You don't even put it in a script or an RMD. You run it once and then your Tidy Census will just work, okay? Then there's the load variables function. The census, decennial census and the ACS are massive, massive data sets. So instead of just loading the entire data set, what you will do is you will load a list of the variables in those data sets and then search through them for the things you want, and then give the selection of variables you want to another function to download them, right? So load variables, you'll just give it a year for the survey that you want, which would be the end year of 5-year ACSs, for instance, or the decennial census year, and then specify the data set you want. It could be ACS 5 for 5-year, decennial, or whatever for census. Then to load the actual data, you will say things like get decennial. This will load the census variables, and if you want, the geographical boundaries of whatever you select. So you give it a few arguments, you give it variables. This is a vector of variable ID numbers. So you just give a name, a vector that has each variable name as its own string. Then you can say geography, which will set the unit of analysis. If you want state level data, tract level data, block group. The Census API lately has had problems giving people block and block group data. They may have fixed block group, but I don't think block is currently working. I haven't checked recently though. You'll give it a year, which is the census year you want for census data, or an end year for the ACS. And then if you want it to give you a geometry, you can say geometry equals true, and it will return an SF geometry column. Similarly for get ACS, same arguments, but you just give it an ACS end year and it gives you ACS data. Okay, so let's see it in action. So we can load up Tidy Census. Here I would, the first time you run it, do Census API key, put your API key here and say install equals true so you don't have to do it again. I did it ages ago, so I don't have to do it. I then say, I want to load up the variables for the 2015 5-year ACS. So this is ACS year data from 2011, 12, 13, 14, and 15. I'm going to save it to ACS 2015 variables. And then this is just to give you an idea of what it looks like. So here I say ACS 2015 variables, rows 10 through 18, every column, and I print it. And we see we get things like a name column. This is the thing you would actually give to get ACS or get decennial to download the variable. These are the variable names. This is the label for that particular variable, and this is the concept that that variable captures or is part of, right? So if you use all the tools we learned last week in the string manipulation lecture, you can search for things in label and concept to get what you want. So if you know you want, for instance, sex by age variables, you could say string detect concept or string detect concept sex by age. And then if you wanted like females, you could say string detect label female, and it will give you only the columns corresponding to concept that contain the word female, right? So that string detect type stuff is invaluable for hunting for variables. If you work with a lot of census or ACS data, you may also just know all your variable numbers, in which case you just punch in the ones you're used to use and you can do it. Okay, so that's kind of like something to play with. You can search through it, find what you want. Okay, so actually getting the data. So let's say I had searched through and I figured out what I want to do is calculate the proportion of people reporting any Black race ethnicity in census tracts in King County, Washington. So I'm going to go ahead and say my King County object is going to be the result of getting some ACS data at the tract level of geography. So I'm going to work with census tract data in the state of Washington and in King County. You could also give FIPS codes here if you're used to working with FIPS codes. I say geometry equals true because I want that geometry to it. I want the boundaries of all my census tracts. And then the variables I want are these two variables. This is just the overall population count in the census tract. And then this is the count of people reporting any Black race ethnicity. So this would include people who also are multiracial, but report Black as one of their multiracial categories. And then here I say output wide. There are two options here. You can have output equals tidy or output equals wide. I actually recommend going with the wide data for this because the tidy data format is a little strange. The tidy data format puts both the margins of error and the estimates in the same column, and I prefer to have a different margin of error and estimate column, okay? So the data that pop out from this in King County, you'll see I have a GOID. The GOID is a code indicating this is the state of Washington, this is King County, this is census tract 323.09. If you're used to reading in these sorts of GOID codes, you know this stuff right away. It has a name, census tract 323.09 of King County, Washington, and then it has the actual values for the variables, okay? So here you'll see I requested the variable B02001 underscore 001E. This is the estimate. E is the estimate. This is 8,249 total population in the tract, but it also has an M column. The ACS is a sample survey. It is not a full count like the census, so it returns margins of error. So this basically says, I forget if it defaults to a 90% or 95%, but basically they say with whatever that margin of error is, there's 8,249 plus minus 457 people in this tract at the end of this 5-year ACS period, okay? So what I'm actually interested in are the estimates, the E columns, and not the margin of error columns, okay? And then you'll see it produces that geometry also. So what I want to do is I don't care about my margins of error in this case. I'm not actually doing any inference on this. So I'm just going to drop my margin of error columns and I'm going to rename my estimates so they're easier to work with and I know what those estimate columns pertain to. And then I want to mutate a new proportion any Black measure. So I say my King County data is going to be my King County data. I say select minus ends with M. This drops any variable that ends with the letter M. In my case, this is just my margin of error columns. If I had 100 of them, this would get rid of all of them without me having to manually pick them out. I then rename my variables so that B02001 underscore 001E is now the total population, and the other one is now the any Black variable. I mutate so that any Black equals any Black divided by total population, which is now a proportion of people reporting any Black race or ethnicity in that census tract, and I take a peek at it. My data frame is now a total population and a proportion any Black, and because this is King County, Washington, I'm not surprised to see a place that has 4.5% black. That actually seems kind of high for me for most census tracts in King County. Okay. So now I have a data frame where one row is one census tract. It contains some measures that I want. It has a geometry column. I'm ready to plot it. So what I want to do is I want to map this. I'm going to say, take my King County data, pipe it into a ggplot. I want to fill my polygons, that is, color them based on my any black variable. GeomSF will draw those polygons, make outlines of them or whatever, fill them with colors, figures out how to do it. I say size equals NA to remove the outlines. This is just a stylistic choice. If you don't do size equals NA, you'll get outlines around every polygon. I then say coordinate SF here, I specify a CRS and a datum. So what this is doing is this is allowing me inside my plot to change the projection it's in. I just swapped to WGS84 because in this particular case, it made the plot look a little bit nicer to be in WGS84 with latitude and longitude coordinates. Datum equals NA is an obscure argument. What this does is remove graticule lines. These are geographical lines like meridians and parallels. If you don't want your meridian and parallel lines drawn on your plot, you can say datum equals NA and it gets rid of them. Stylistic choice, you don't have to do it. I then put because I'm picky about colors, I put a color scale on my fill, give it a minimal theme and a title. So this is what that plot looks like. So this is a plot of the proportion black in every census tract in King County. So King County is a pretty big county. It contains all of the city of Seattle. The city of Seattle's northern border is the northern border of King County over here, kind of. It's actually, yeah, right around there. Extends down here to the bay. Seattle kind of breaks off right around here and then has the additional cities below it down to everything just north of Tacoma. And then you have a lot of these massive census tracts, which are essentially the Cascades where very few people live, right? Okay, so on this particular plot, what do you see that is annoying or problematic about this plot? Does this look like a sky view of King County to us?
The water is filled in as well.
Yeah, right. So you look at this and you're like, okay, where's Lake Washington? Well, the thing about it is Lake Washington is right here. It just so happens that the US Census tracts extend out and meet in the center of Lake Washington. So you get these really big census tracts that have nice smooth lines between them because they've just evenly divided up the lake between its shores, okay? So this does not look like, or at least doesn't allow us to easily pick out where things are on the east side. I can't tell Bellevue and Kirkland apart from Seattle over here very well because the lake is filled in as if it was land. I don't like this. It's purely an aesthetic thing, but what I want to do is I want to add some water into here. We've got water for Puget Sound because the census tracts end on ocean-like shore here, but they don't cut out the lakes. Let's cut out the lakes and rivers to make this look pretty. Okay. So to do this, I have written and put together a function here, which is partially borrowed from Stack Overflow code. This is a function that will remove water from anything that you want to remove water from. So if you're working on a similar sort of project or mapping thing and you want to remove water from your census tracts, don't write this function yourself, steal mine because it works pretty well. Okay, so what this is a simple little function that will download the appropriate boundaries of water in some given state and county and subtract them from some existing SF data frame. Okay, so this function has a bunch of functions in it, which I haven't told you about and are somewhat complicated. So what I'm going to do here is I'm going to create a function called st_erase. The idea here is that this will take some data frame I'm working with, X, and subtract from its geometries something I give to it, Y. Could be water, but it could be anything else I want to subtract. Maybe I want to cut out a bunch of tracts or something from a state. Do whatever you want. How this works here is it takes st difference of its input versus this thing over here. So what a difference does is a difference is geospatial subtraction. It takes the thing over here and removes from it the things on the right side. What is this thing on the right side? So it takes the y input of the function, it st combines it. So what this says is whatever you give to y here might be a data frame with many, many, many different geometries. ST will combine them all sort of into a single geometry because I only want to subtract like one thing. I don't want to do pairwise subtraction. I want one thing yanked out everything else. ST union unifies them all into a single polygon, because I want to subtract one polygon, not multiple polygons. And then ST make valid is something that's important. If you combine a bunch of polygons together, but they produce some physically impossible boundary, like you have some boundary that intersects with itself, maybe it has a loop in its boundary, you need to tell R that you need to fix those things, because you can't subtract an impossible object from a possible object in sort of GIS terms. ST make valid just says, look and see if you see anything funky in this object I'm giving in. If you see something funky, unfunky it for me, okay? So it does all that, and then it just subtracts this whole thing from our thing on the X. Okay, we now have an erasing function. Then what I want to do is I want to grab something to erase from my King County data frame. So I want to get all the water in King County. To get the water in King County, I'm going to use this package Tigris. The secret to Tidy Census is that Tidy Census is not the package that gets the geographical boundaries from the census. The package is actually Tigris, which gets tiger line files from the US Census that define all of the different geographical units in the United States. Tigris contains functions like this. I can say, Tigris, go into Tigris and get the area water function, get water areas from the state of Washington and in King County, and return to me an SF object. What this will do is it will get every census identified body of water in the state of Washington. Every body of water would get its own row in the data. This is also useful if you actually want the bodies of water. You can download them here and it gives you all the bodies of water down to pretty small units. It gives you all the like mountain lakes and everything, okay? Then I want to say, take my King County data and erase from it all of the water. This st_erase function takes care of formatting KC water properly to do the subtraction, and I produce a new King County no water data frame. It keeps all of our own columns and everything like that and generates a nice no water data frame. So here's a question over here. Does this only work for mapping? For example, if I wanted to get the surface area for each census tract, do I use this to subtract the water from the tracts? Yes, absolutely. This will literally remove them from the polygon, so you could then recalculate their area and it would be the area minus the water. It actually modifies the underlying data. So if you don't want to do it just for mapping, you want to do it for anything, it's the exact same thing. Yeah, not just for mapping, but for any geospatial operation. And I've actually done this myself for that exact reason. I don't want to adjust crimes by the size of the tract, including water. I want to adjust the number of crimes in tract for area by the actual land area. Though actually, I think I was adjusting them for the actual ground area. So removing buildings from my street crimes and stuff, which was somewhat more complicated, but same deal.
I'm sure this is like beyond, a little bit beyond this lecture, but like instead of erasing the water could you write a function that makes the water a different color? Like if you just want the water to be blue or something in your map?
Yeah, the way to do that would be to make it a separate object. And the easiest way to do that would be to chop out all of the water from the actual tracks and then add in the new rows with the actual bodies of water. Probably be the way I'd do it.
Yeah, makes sense.
Anything else? We're going to see how this looks. It's going to be fun. Okay. So this is the new map, the exact same plot replotted, but with all the water removed. And you'll see this is a much prettier plot. So regardless of what you're doing with it, if you were going to put this map in a blog post, a journal article, or something like that, you might as well just remove that water to make it look nice. And this is something I always tell people in like little talks I give, presentations, workshops. If you're writing a blog post, a journal article, anything like that, people fucking love maps, right? People really love maps. So if you're doing like a talk somewhere, a job talk somewhere, if you can find some way to plot the data you're working on and put it on a map people recognize, especially if you're going to give a job, let's say you're going to give a job talk at some university in like New York, plot something on top of a map in New York. People love this local stuff. They eat it up. And maps resonate with people the way almost no other visualizations do, because the maps represent something they interact with on their daily basis, the actual like places they live and they travel through, right? I highly recommend recommend whenever possible, if it's useful in any way, put a map in something. People love maps. The person who actually, I think, first told me this was Chris Adolph told me this, and then it was reiterated by John Wakefield in CSSS. So they're like, oh yeah, if you got any excuse, put a map in there. People love that shit, right? And I'm just like, I will live by it, and I do it all the time. I stick a map in every paper I can, and reviewers, when editors come down to it, I'll tell you, the thing they want to remove from it is like tables of coefficients, but they will leave the map in your article. They'll love it. Okay, so this is a much better map, right? This looks good. You can kind of see how things actually line up. It looks great. Okay. So next thing, let's adapt this code to do this with an entire state. So instead of working with King County in Washington, my roommate is a native of Rockford, Illinois, and lived in Chicago. So I like to use as an example, the state of Illinois. Okay. So what I've done here is I've taken the exact code I just used for everything in my King County example. And the only thing I've changed is instead of saying I want King County, I just say I want state Illinois. Every other piece of code is exactly the same. So we're still going to map the proportion black, just going to use the entire state of Illinois. The plotting code is also exactly the same. And now we get a map of every census tract in the state of Illinois. Right? Well, there's a lot of census tracts in the state of Illinois, so you can see it gets down to really tiny little granular areas like that. This is a cool map. One thing that I like about this is it really shows you the sort of unique segregation patterns of like Black people living in the Midwest, right? It's highly urbanized population concentrated in particular areas. This is Chicago up here. You can see south side of Chicago over here, barely any over here like that. Sort of a very concentrated population. I'm a demographer, so this kind of stuff is totally up my alley. Some people find it boring. I'm totally into this, okay? So if I look at this map though, I only know that this is an urban area, this is an urban area, like, you know, this is an urban area. I only know these are urban areas because I kind of know what the interior of Illinois looks like, right? So maybe what we might want to do in a plot like this is add to it the actual urban boundaries so we can see how this sort of segregation and concentration looks like in the state of Illinois. Let's grab some urban boundaries and huck on another layer. Okay, so like we do with anything in ggplot2, right? We can add additional geom-sf layers to the same plot. You can have as many geom-sf layers as you want in a single plot. You can just keep adding them on top of each other if you have more data to put onto it. You don't have to merge it into the same data frame. We can just give it a new data frame, okay? This is really useful for doing things like maybe you plot a bunch of polygons, be they precincts, tracts, states, but then you want to do things like add points on top of them. Maybe you want to show where cities are in all the states. Maybe you want to show where crimes are in police beats, something I do all the time. Maybe you want to add lines. For instance, something I've done a bunch of is maybe I want the whole street grid of Seattle plotted on top of the census tracts so I get a feel of how the census tracts line up with natural boundaries in Seattle. Another things you might want to do is maybe you want to add outlines or highlights on top of your map, maybe elevation contours on top of some sort of administrative map, or in this case, maybe you want to show urban boundaries on top of existing administrative demarcations. So let's see how we do that. We can use that Tigris package I mentioned before to download the urban boundaries that are, so the urban boundaries defined by the US Census and add them to our map. All I need to say here is, let's get every urban boundary in the United States. Urbans, this Tigris urban areas, I don't think allows me to specify a state. So I just grabbed the urban areas for every place in the entire United States, which I'll note includes overseas territory. So it'll be a funny looking map if you plot it. You'll get shit in Guam and stuff like that. So I say, give me all the urban areas. If you're running this code along with me, this might take a little bit of time to run because it's a reasonably large file. Okay. And then I can glimpse this urban's data. I take a look at it. We see things like urban area of Tucson, Arizona, Altairosas, California, Davenport, Iowa, blah, blah, blah. The only thing I care about is stuff in Illinois. So I look at the format of this where it all ends in state names like this and they're capitalized. And I just say, I'm going to get only the Illinois urban areas by taking my urbans and filtering down to string detect in name 10, that's the name column here, to capital IL. I don't think anything outside of the state of Illinois is going to be represented by capital IL unless I pre-capitalize these names. I didn't, and it works. So we can filter down to Illinois. Here's a question here I missed. Is there a function to create dots, points of different sizes to represent densities in an area? Small dot equals low density, large dot equals high density. Yeah, if you make the density a attribute of your data, so for each one of those simple features, each row, it has a density, like for instance, a count as its a column in the data, just map AES size equals that column and it will make it bigger or smaller. So the easiest thing is just to generate the data that way and map it onto it. If you are actually working directly with the densities, like literally mapping it onto a dot is going to be kind of different and hard because a density is an attribute of continuous space, but the dot is a discrete unit. I would recommend calculating that thing for like a discrete unit and then mapping that onto a size. Okay, next one. Let's add this to our existing plot. So I still have my, my state data, the same ggplot, the same geomsf, but I've added a second geomsf call. I say here, geomsf, new data. So we're going to work with different data on this particular geomsf. The data is my urban IL object. I'm going to say here, color equals black. What I want to do is I want to draw a black outline around urban areas. I say fill equals NA because I want the polygons empty. I want an outline, so I don't want to fill the polygons in. Size 0.1 is going to make a thin line around them. So we're going to get a thin black line drawn around our urban areas. And then this is important. Inherit.aes equals false says do not inherit any AES specified in the top level ggplot call. So I don't want fill equals any black because I don't want my polygon filled with anything. Instead, I want it filled with NA. Otherwise, the plot is exactly the same. Now, we have our state plot of Illinois, but with a thin black outline showing every census recognized urban area in the state of Illinois. And this again shows our segregation sort of and concentration story I mentioned earlier. We can see that all of the concentrated spots of people who are self-reporting as any black in the US or in the ACS are basically all located in urban areas. The only exception is this one down here, and I think it's actually because of either a bordering urban area or I can think of one other reason it would be, but I'm not going to comment. Anyway, this is a general, like this is the greater urban boundary of Chicago, which extends all the way up to like Kennewa or whatever, all the way up here, right? Kenosha? I forget which one. Anyway. Yeah, so this is something cool. You might want to add another layer like this. Think of the possibilities of layering on different geospatial data, and you can kind of pretty up your maps in different ways, right? So kind of a useful, fun little exercise. That's the last thing I have on mapping for today. So just going to say there is an optional homework. So we haven't actually finished up homework 6 part 2 yet because I delayed the lab till Monday. There is this optional homework here. I say it's supposed to be submitted next Tuesday. Just bump that a week back, right? So it's like the last week of the the end of finals week, basically, or whatever. Turn it in if you want it. The points in this class don't really mean anything, so you don't have to. But it's a fun experiment in sort of messing with some geospatial data. It's the restaurants data, so you can kind of have fun mapping where all of like the places with the worst inspection scores are in Seattle. My favorite bad inspection scores in Seattle is, as it turns out, some of the filthiest kitchens in the greater like King County area are the fraternities on Frat Row outside the university. They just have some poisonous ass kitchens. Like it's some toxic stuff going on there. You're like 70 violations in a frat kitchen. I'm just like, good Lord. It's like the next pandemic is going to come out of that area of the city. Okay. Anyway, it's an optional homework. Do it if you want. It doesn't have a peer review associated with it, but I'll take a peek at it myself. So anyone have any questions? Done a little bit early?
Yeah, on the previous slide with the outlines of the urban areas, is there a way to like clip the outlines so that they aren't outside of the state boundaries?
This is what that st_erase function can be used for. So what you'd want to do is you could go grab, you'd essentially want to grab the boundaries of the surrounding states. probably, and then combine them all into one geometry and subtract it from this urban boundary layer.
Okay.
Yeah, be the easiest way to do it that I can think of. There's sort of other weird things you could do. For instance, you could get the combine Illinois all into one geometry and then use ST buffer to generate like 100-mile buffer around it. And then subtract the original Illinois state from it. And so you'd essentially have a donut, and then subtract that donut from the metro areas. Basically, it's more of a mental game than anything to figure out how to come up with the objects you want to add or remove. But it's kind of fun. It's kind of neat to be doing like subtraction and stuff with images instead of like numbers. I find it's very entertaining to play with.
I have another question about the census data. Oftentimes I'm looking to like combine tracts, say like within a mile of some project. These are for grant applications. Mm. I'm wondering if there are easy ways that you've done that to look at, like, for example, any black within these 3 census tracts in Seattle.
Yeah, so there's 2 parts to that. Is one, if you want to combine the census tracts together, you can aggregate them using summarize. Like you just group on things, come up with some variable that determines them, and summarize and group on it will join the units. And you can actually join the geometries too by saying like ST union the geometries. It will combine those census tracts into one geometry. So if you want to make like clusters or something. The other part of that is identifying and selecting those. So saying they're from a distance. There's a couple different ways you can do it. So distance can mean a number of different things when you work with polygons. So you could be like anything within, so if you have some point, you're like, I want any census tract within, let's say, 1 kilometer of this point. Well, that distance could be a distance to any edge of the census tract, or it could be something like the distance to the centroids of the tracts. So you could obtain the centroids, like the center of mass point of each of those ones, and be like, I want any tract whose centroid lies within 1 kilometer of this point. And you would just you could calculate the distances and create groupings using ST distance. And each one would give you you'd essentially get a matrix that would be of binary values where for each point that you calculate a distance from, you would have like a row is the dots you're calculating distances from, the columns would be every census tract in your data set, and a 0 would be outside that distance and a 1 would be inside that distance. And then you could use that matrix to do some subsetting or manipulation of your data. So you kind of have to figure out how you want to define the distances, but it's all doable within the SF package using like ST distance is the main way to do it.
Cool. Yeah, thanks.
Sure. Anything else?
Can I ask quickly, and you sent an email out earlier about the updated RStudio. Is there any downside of updating RStudio? Is there any like risk? I remember you mentioned at one point, like updating, it might change some libraries, but I couldn't remember if that was RStudio or just actual base R.
That was R. So R 4.0 is probably safe to upgrade to now, but usually with R versions, I give them about 5 days to a week when they pop in case they break something. RStudio is not like that. RStudio as a company is super conservative about doing their final releases. They don't release anything until it's basically bulletproof. I've been using development versions of RStudio 1.3 for like nearly a year. And now they finally released it. My development versions were always stable. I already upgraded. As soon as it popped out today, I upgraded my RStudio to it. It works perfectly. And the spell check functionality is actually really nice. Like it just works. It works just like it would in Word or something like that, except it doesn't tell you that all these data science terms and functions are incorrectly spelled and stuff because it knows these things. It's great. No, I would upgrade immediately. There's no downside.
Thanks so much. And then also a couple slides back, and this may be like I feel like you've gone over this before, but before when you were defining the function that removed water,
yeah,
you coded it as, so function xy, and then x, and then the actual like what the function is doing. And then when you actually like applied the function, you only gave it one term.
Yeah, you see, what I've actually done is I've written a function that takes its first argument as a data frame, and its second argument is also a data frame that I want to subtract things from. So what I've actually done is I've piped the King County data into st_erase. So x is the first argument. So it's made King County the first argument of st_erase.
Okay, no, that's super. Okay, thank you so much. Yes, okay, perfect.
Yeah, so I like to, when I write functions, I kind of like to make them often tidy style, so they take a data frame as their first argument, so I can pipe shit into them. Just the way I like to, my brain thinks. You could also, equivalently, I could have written this in such a way that would be used in mutate instead of being like having a whole data frame piped in. You could do that too.
Perfect. Thank you so much.
Yeah. Okay, anything else?
Super small detail question, but it seems like the colors aren't like typical names like blue or red. It's like, yeah. So like, do you just like Google and there's like a chart of the colors for you to reference to find out what those are?
So if you know hexadecimal, I will just know colors that I want to pick out of that, but you can Google and get color palettes and things for it. So I am very picky about coloration. So actually what I did here is I selected my highs and lows so that my high value is the same color as the color border of my slides, which was actually this top end color up here is approximately the color border. It's nice if you want to specify exact palettes. If you, you know, basically all zeros in hexadecimal here is black, right? And so you kind of know how to pick them out. And this is just giving it a little bit of blue and red, so it's purple. Well, not blue, a little bit of green and red. Yeah, normally you just look it up. You can Google and there's tons of good palettes out there for constructing things. This is sort of a thing I do because I'm a very picky person. You could just give normal values, but hexadecimal codes are really nice if you wanted to match an overall theme. So I like my slides to have sort of this cool, like cool as in color tone, cool blue to purple sort of thing. So I've picked ones that, you know, don't have many warm tones in them. It's just pick some hex codes. And there's actually some great palette pickers. I think I may actually have one I recommend. Let me see. In the ggplot one, I thought I had one linked. I must have removed it. I used to have a thing that would provide ways of generating really nice uniform palettes for data visualization, which are a little bit different than making like pretty website palettes, because you want to make things that have high differences between them, not just in the color space, but also in like that are colorblind friendly and stuff like that, which is kind of nice. Yeah, but yeah, hex colors, I typically specify almost everything in hex colors so I can be real specific. And it also means that you can kind of uniformly use those colors across like everything. It's kind of nice.
And then a kind of a follow-up on that for like formatting stuff. Could you specify, if you're doing like a gradient on the scale, could you specify like middle colors as well instead of just low and high?
Yeah. So you can specify scale fill continuous has a an alternate version that also has a middle point. So it's a kind of like a bidirectional gradient, which is really useful if you have things that have if you have ratio data with a definite zero. If you've got a definite zero, I like to make like one color in the middle, like black or something like that, and then it diverges maybe red in one direction and like not green in the other direction, but like blue or something. Yeah, you can. I think it's actually. Let me just check because you have me here. I think it's scale color gradient 2 probably.
Yeah, because like what I was kind of thinking of is, for example, in the elections one, if you had the percent Democrats having like 0 be red for Republican and then like something like that.
That's a good idea. In Seattle, it wouldn't do anything for you because
they could, or like, could the middle be more purpley or something? Yeah,
you absolutely could, and that's exactly the way that you display that if you're going to present to people. That's a brilliant idea. That's the way to do it. So you see here in I think it's not scale. Yeah, it is. Scale color gradient 2 takes a low, a mid, and a high, and you can select the midpoint manually for it. And so this is exactly that. If you have the voting data, you set the like 0.5 as the midpoint, and then put it low, mid, medium, high.
So then you do like low red, mid purple, and then high blue.
Yeah, and if you did all of King County instead of just Seattle, you'd absolutely want to do that because it gets red as soon as you get outside the city limits, basically. Yeah, no, great thought, and absolutely. Okay, anything else?
And then I'm just kind of thinking of stuff I've done on GIS and how I might do this here. So say you had something where instead of like a gradient where you're showing like percentages or something, you had like unique, in GIS we say like unique categories, like you wanted to, I don't know, like show, like you have maybe points and you wanted to have them unique categories, like a name of something. Is there a way to do that? Like, for example, I've made a map in ArcGIS where I have like property, like parcels associated with a particular church, like they own different parcels. And so my unique categories are anything associated with church A, and then the other unique is church B. And then so the parcels are colored by that way.
Yeah, and that would just be like a character or factor column in your data, and you just provide fill equals that categorical variable, and it will generate the legend as any categorical variable.
Okay, yeah.
All the same tools we've used for everything else. Okay, so here's a question in here. To expand on Veronica's question, for more distinct data or larger ranges, are there ways to select more color? Oh yeah, had the same thought. I don't know if you can go beyond 3, but also gradients get really wacky beyond 3 colors anyway. So 3, I think, is the max ggplot supports, but you can do 2-dimensional color gradients. So instead of a color gradient that goes like left to right, you can imagine it occupies a square plane. And so one color runs on the x-axis and one runs on the y-axis. And so in different parts of it, it's a different combination of the 2 of them. You can absolutely do that kind of color space. And I forget the exact way to do that. But there is a ggplot scale for it that does, gradients across 2 dimensions. I don't remember where it is though. It's commonly used if you want to plot 2 variables simultaneously on a single color aesthetic. I've seen a lot of demographers doing this lately. I think it's stupid and you shouldn't do it because it's really hard to read 2 colors simultaneously, but people love it. And so they just do it all the time. And then you just end up with these plots that are really hard for your brain to wrap around. Anyway, bad visualization style. Take Chris Adott's visualization class. Learn why not to do those things. Okay. Okay, anything else? Yeah, this is a fun lecture. This is some cool stuff. And people tend to like, you might not realize R has all this power to GIS stuff. There's a lot of people who do 100% of their GIS work, and they do a lot entirely in R. Like John Wakefield over in Stats, who's like a really renowned geostatistician. He basically does everything in R, regardless of like, somebody's just like, it's the way to do it. Every once in a while, there is something worth going back to QGIS or ARC for, some things that are sometimes faster. The weird thing is R is actually, in some spatial operations, very fast. In some spatial operations, really slow. It just depends whether the code is optimized or not. Yeah, but I mean, I don't do anything in any outside platform because it's just not necessary. But you know, once in a while, it's nice to visualize and stuff. Like if you want to, especially if you want to do any kind of like editing things, maybe you need to actually draw shapes of some kind. You're not going to be doing that in R. So that's what I would use it for. Like I've got sometimes kind of qualitative data that I need to map an area out. Like so I'm doing some stuff on sweeps of homeless encampments in Seattle, and there isn't actually any ground data mapping these things out. So I have to I'm going to have to get into QGIS and manually create the shapes for it and then bring them in. That's like what I would use it for, because R doesn't have a nice interface for that. But it's basically data creation and maybe looking at some stuff. Though on the flip side of this, one of my really good friends, Tim Thomas, who used to be at eScience here and is now runs a lab at Berkeley in evictions. He used to just fluidly move back and forth between QGIS and R for all stuff because he came from a surveying background. And so he'd just be like, whichever one I can think of to work faster in is the one he'd go to. Same thing. If you already have a bunch of GIS skills like that, don't discard those ones. Work on whatever works fastest for you. And the nice thing is these things all speak to each other in similar languages a little bit. Those scripting in like QGIS and ARC is mostly done in Python, but you know, you can talk back and forth with each other. Work on what makes sense to you. Okay. Okay, so I think that's it. We only got 1 lecture left. I'm going to be sad when we all part for the term. But I'll see everyone on Monday for homework 6, part 2's lab. Okay, bye-bye, folks.